We're very happy to have Denis Auroux today, who will tell us about Floer-Theoretic corrections to the geometry of moduli spaces of Lagrangian Tori.
Okay, thank you very much. Thank you for the invitation. And apologies for the long title. It's a sneaky title that is there to kind of avoid saying the word mirror symmetry, even though that's what the talk is about secretly. But I will try to formulate it in a way. Well, I mean, you'll see. Sometimes I will say moduli space of Lagrangian Tori, and sometimes I will say, you know, mirror space, and that's kind of the same thing. So I shouldn't cross that out, maybe. I should instead say equals mirror space. Anyway, okay, so let me start by, anyway, motivation will have the word mirror symmetry. It's kind of easier that way. So the Strominger-Yau-Zaslow conjecture from 1996 proposes a general construction of mirror spaces to a given symplectic manifold. And what it says to us is basically mirror space is a certain moduli space of objects of a Fukaya category supported on Lagrangian Tori. So the construction proposed, I mean, it's not like a sure recipe, but it says here's what you should try to do. You start from a, I'm going to say Kahler manifold because we don't know any, well, we know one example that's not Kahler. That Kahler manifold might be Calabi-Yau already, or it might become Calabi-Yau after you delete a union of complex hypersurfaces. So I will assume I can remove a union of hypersurfaces that I will call D, representing the first Chern class of my manifold, so that the complement is Calabi-Yau. So this is called a log Calabi-Yau pair for people in that field. So the suggestion is that we should start from a Lagrangian torus fibration on x minus d over some base b. And Strominger-Yau-Zaslow, for various reasons, wanted it to be special Lagrangian. That's very hard to do in practice, and we don't need it. So instead, I will mostly ask that the fibers have vanishing Maslov class in x minus d, so that you have a z-graded Floer theory in x minus d, and generically unobstructed in x minus d, and so on. You know, so things for which we can do reasonable Floer theory. So the proposal, this is not the language in which SYZ said it, but this is like the reinterpretation after many years of homological mirror symmetry and all that. So the uncorrected mirror of x minus d is going to be a space of pairs consisting of f, nabla. Nabla, it's a weird name, I don't know why I used that. So f is going to be a fiber of this Lagrangian fibration. And we want to equip it with a unitary rank 1 local system over it. So what that means, a rank 1 local system is just, you know, something that looks like a copy of whatever coefficient field you're using. I'll say more about that in a moment, but I will secretly think of Novikov fields, okay? And a local system means that globally this is a non-trivial, possibly non-trivial flat connection on a trivial rank 1 line bundle. So what it has is it's going to have a holonomy around loops in the fiber. So anyway, I'll get back to this on the next slide. Okay, right now this is motivation, but the goal will be to parameterize something that before has been called the dual torus of a fiber F. Maybe you've heard the slogan mirror symmetry is torus duality, and this is kind of, you know, some version of it. So what we will see is that this space is always going to be nicely something analytic, locally modeled on an algebraic torus, k star to the n, over whatever coefficient field you use. So anyway, so you should think of that as a moduli space of Lagrangian Tori plus flat line bundles over them in x minus d. And then stage 2 is that the actual geometry that you want to use is not the classical geometry of a moduli space of tori, where everything is governed just by topology, and the only information about how you move your Lagrangian tori is basically the amount of flux between them, how much symplectic area is swept when you move from one to the next. And you want to bring in instead holomorphic disks. Including holomorphic disks now in X, not in the complement of D anymore, because we are not going to try to stay just with X minus D. We want to get back to X. And so the slogan here is we are going to try to pass from the classical geometry of spaces of Lagrangian tori to instead the geometry of a space of objects of the Fukaya category corresponding to this tori. And so the way holomorphic disks intervene depends on really the Maslov index, because they will disks of different Maslov index will have different impacts on the Floer theory. So the starting point, disks of Maslov index 0. So one small note, we have tori of vanishing Maslov class in the complement of D. And so that means, and D is representing the first Chern class, that means Maslov index in this talk is going to be always twice the algebraic intersection number with D, just because of how Maslov class is a relative first Chern class. And so these are going to have a role that they will deform the analytic structure of this space that we're trying to build. And I will tell you how more precisely. But basically the story there is that bubbling of disks causes what's called wall crossing jumps in Floer theory, and you're supposed to correct for those by gluing pieces of your mirror space or of your moduli space in a modified way to account for that. So you could say in more symplectic language, this has to do with induced continuation maps on moduli spaces of weak bounding cochains in Lagrangian Floer theory or things like that. And then, so just because this will make our life easier, we should think of disks of non-zero Maslov index. The most obvious ones will be the ones of Maslov 2, the ones that intersect D once. So these are disks that you don't have in X minus D, but when you bring back in this hypersurface D, they get added back in. They are the simplest ones of that kind. And what they will do is they will produce for you an analytic function on this space. And in the world of mirror symmetry, we say this makes the mirror a Landau-Ginzburg model, which just means a space with a function on it. And so the superpotential and its derivatives govern a lot of the Floer theory of a tori in X. I mean, for example, a Lagrangian torus in X minus D typically will become the trivial object Floer theoretically in X, unless it's a critical point of its superpotential. So objects remain non-zero, more or less, if and only if they're critical points of a superpotential. And so now there's something new, which is why I'm giving this talk in 2024, which is that when they occur, negative Maslov index disks actually cause this picture to break down a little bit, not in a way that's completely dramatic, but in a way that's a bit surprising at first, in that the space you're trying to build is actually no longer an analytic space. And we'll see exactly how this happens. So that's the main point of the talk. And so you may also ask, wait, how can the intersection number with D be negative? Because I seem to be nicely in some Kahler holomorphic setup and so on. I should have positivity of intersection between a holomorphic disk and a complex curve or hypersurface. Well, the problem occurs if D contains spheres of negative Chern number, because then I can have configurations consisting of a disk that hits D together with a negative sphere in D, and the union of that may well be regular as a stable nodal disk, and I may have to count it. And so the other part of the talk is going to be convincing you that this actually happens in real life. Okay. All right. So, and feel free to interrupt with questions at any time, but maybe I should start again, telling this story more slowly. That was the introduction slide. So first, we are going to talk about the uncorrected moduli space of tori. So we start from a Lagrangian torus fibration on x minus d. And we want to look at pairs consisting of a fiber of this fibration. Now, in real life, there will be singular fibers in your Lagrangian fibrations. They're not really the main point of today, so I'm going to ignore that. And I'm just going to, for now, restrict only to the smooth fibers and ignore the singularities. There are ways to deal with those. I will not tell you very much about that. And then together with, so my local system, I will think of as a homomorphism from the fundamental group of FB to U1, the unitary group of rank 1, over my favorite field, which has some kind of norm. So this is also H upper 1, the first cohomology of the fibers with coefficients in U1. So it wouldn't be completely horrible to pretend that we can use complex numbers and then this will be usual U1. But because we'll be, after all, dealing with disk bubblings and things like that, it's safer to think of a Novikov field. Okay, so remember, as coefficient, we'll use the Novikov field in one variable that we'll call capital T. The coefficients in front of the power series in T can be in whatever field you like. I'm thinking of complex numbers. It's probably easier to have something of characteristic 0, but I don't know if you need it. Probably not. Anyway. Doesn't really matter. The exponents are real, increased to infinity as usual in Novikov fields. And then what is U1? So U1 is the elements of valuation 0. So this is the elements where the leading term is some coefficient A0, that's non-zero, plus, and then there's terms, you know, with positive powers of t. Okay, so I claim that this space of pairs has a natural structure of analytic space. And one way to describe this is to give local coordinates, give local coordinate charts on it. So my favorite way to build local coordinate charts is to basically exponentiate symplectic area. Okay, so if I fix a base point B0 for a little region of the base of your fibration, then connect that to some other point of your choice B by some path. Also fix a basis of the homology of a fiber. You don't need to, but it kind of saves some headaches in the morning. It's the morning here. So, and then for each of these loops gamma I, when you push it from the reference fiber to the moving one, you get a cylinder. You can take the symplectic area of that cylinder, and that's something I will measure. I will take that power of the Novikov parameter T times a unitary element, which is going to be just the holonomy of my local system along that loop. Okay, and so these will be local coordinates. Another way of saying it, of course, is that the flux from the reference fiber to FB gives me a class in H upper 1 of the fiber with real coefficients. And I have here something which is in H upper 1 with unitary coefficients, and I combine them into H upper 1 with coefficients in the Novikov field. Okay. So why is this analytic structure, so then this locally looks like a piece of K star to the n. And if I change my basis of H1, or if I move my reference fiber, I will just change coordinates by some monomial coordinate transformation. Like each Zi will become some monomial in the other Zi's, a Laurent monomial. Okay, so why do I care about these particular quantities? It so happens that these are exactly the kinds of weights that one should use for counting disks in Lagrangian Floer theory with Novikov coefficients in the presence of local systems. So if I have a holomorphic disk with boundary on the fiber FB, representing some class beta in relative pi 2, then Floer-Theory tells me that I should be counting it with a weight which is T to the symplectic area, that's usual Novikov coefficients, and times this holonomy along the boundary is how we put in local systems. And these quantities are automatically monomials in my local coordinates z1 ... zn. Sorry, I should have said maybe Laurent monomials. Right? The exponents of z1 to zn have to do with how you take the boundary loop of your disk and you expand it in the given basis of h1. And so the effect of this is Lagrangian Floer-Theory has an analytic dependence, we should say locally analytic dependence, on the position of your fiber and the local system. Essentially automatically, because as long as the disks you count or strips you count don't change qualitatively, all that changes is that their weights vary, and their weights vary by analytic expressions, and therefore things are analytic. And so this is how Fukaya, followed by Abu Zaid, and then others, have started this whole family Floer-Theory approach to mirror symmetry, saying, when I do Floer-Theory of a fixed Lagrangian or fixed collection of Lagrangians with this moving family of fibers with local systems, Floer-Theory will output for me things that are analytic sheaves over this moduli space. And so I can transfer the Fukaya category of X to coherent sheaves on the mirror space. All right. Sorry, maybe I should pose questions so far. No? Okay, so next we need to talk about corrections from disks and how Floer-Theory obstructions show up. Okay, so as I said, if there's no holomorphic disks, we have found a nice moduli space of objects of a Fukaya category of X minus D with a natural analytic structure. And then in the presence of holomorphic disks, there's going to be a deformation of how Floer-Theory works. And this deformation, the most visible part of it, is that Floer-Theory can become obstructed. So there's supposed to be something called M0 of a Lagrangian, which is like what comes before the Floer differential product and so on. For each Lagrangian, this should be an element of a Floer complex of L with itself. What that means exactly depends on your chosen technical foundations. And the way we build it usually will be from moduli spaces of disks with one marked point on the boundary, mapping to the space X with boundary on the given Lagrangian. So you look at holomorphic disks in a given homology class, mod reparametrization fixing the boundary marked point, and this moduli space has an evaluation map at the marked point to the Lagrangian. And so this moduli space has expected dimension n-2 plus the Maslov index of the class beta. So in some fictional version of Floer-Theory, M0 would be a sum over all possible homology classes. And then you try to define some kind of stable map compactification of this moduli space of disks, and then you regularize it, and then you define some virtual fundamental class or something, okay? If you don't want to dig into that, there are also Floer-Theoretic Morse-theoretic models, like a version of a Pearl complex from Charest and Woodward that works very well for this. But anyway, so you still should think of this. You look at where basically the boundaries of all the holomorphic disks in the class beta can land. You use that to build a chain on L. You put a coefficient, which is this weight Z beta next to it. And that gives you a chain or cochain on your Lagrangian with coefficients in K because of these coefficients that we've put there. And its cohomological degree will be 2 minus the Maslov index, just because that's the codimension of the evaluation chain you expect to get. And this, by the way, tells you why we don't care about disks of Maslov index more positive than 2. Those don't contribute to M0, and basically it's not clear that they're needed to actually understand the deformation. Once we pass to Hochschild cohomology later, they would end up in negative Hochschild cohomology, which usually vanishes. Okay, so what do we expect this M0 to do concretely? So first, we expect that actually Maslov index 0 disks, the ones, for example, that avoid the bound of this divisor D, won't happen for the generic fiber. They will only happen along a union of so-called walls of codimension 1 in the base B. Why? Well, part of it is because of tropical geometry. Part of it is mostly still wishful thinking. But this is what happens in practice. Okay, so in practice, we see that Maslov index 0 disks occur along a union of complex hypersurfaces in your ambient space, and those want to project to be along something that's kind of skinny, like a tropical hypersurface in B, as long as the complex structure on B is on X is sufficiently stretched towards the tropical limit. Now, because complex things don't quite project to the tropical thing, these are usually thickened codimension 1, so they're slight neighborhoods of a codimension 1 thing. Compounding difficulties, there's usually countably infinitely many such walls. So of course, when I say most fibers don't bound disks, that's fiction, or it's only true up to a certain order or something. But outside of the walls, to the extent that this can happen, then your fiber is going to be weakly unobstructed, which means the smallest Maslov index that you encounter is going to be 2, corresponding to disks that intersect D once. And then, just by inspection, this makes it happen that M0 is going to be a multiple of, by 1 I mean the generator of H0. So you could say it's the fundamental class as a cycle. And then there's a coefficient in front, W, which we call the superpotential, and which you can rewrite more directly as a generating series for Maslov index 2 disks passing through a given point of your Lagrangian. This is what degree of evaluation map does. It means count how many ways you can make this pass through a generic point, and with these coefficients, Z beta. Okay. Now, on to wall crossing. So this superpotential function is going to be a nice analytic function over the domains in your moduli space where you don't have any jumps in the counts. And the jumps occur when Maslov index 2 disks get affected by bubbling of Maslov index 0 disks. So concretely, what you might have is that you have a certain holomorphic disk with boundary on a given fiber of your F, and as you move, as you hit the wall, your disk breaks into a union of 2 disks. I'm thinking of the red one alpha to be Maslov index 0, the one that kind of lives only on the wall, and then your big disk has disappeared, so the smaller component has survived, and of course that one also existed before. So on one side of a wall, you have a disk in the class beta plus alpha, one in the class beta. The other one, you only have one of the two. And so when you count those, the superpotential has changed by this kind of discontinuity. So what we know we should do there, when we have a discontinuous function, your students in like first year classes, they worry about how much the function jumps. And this is not what we should do here, because instead, the theory tells us, I think this probably goes back to Fukaya Ota Ono, is instead you should ask, how much has the domain of your function jumped? In the sense that this is the kind of discontinuity that you can cure not by changing the values of a function, but by changing its domain, by making coordinate changes on the pieces of your moduli space. And so in this case here, what you should do is replace Z beta by Z beta times 1 plus Z to the alpha. And of course, in general, there would be more terms from other disks. So in general, if you have a wall of disks in the class alpha, you expect to have some, sometimes called the wall crossing function, or the slab function by Gross and Siebert, which is going to be some power series in Z to the alpha. This power series basically tells you how many disks in the class alpha and in the class 2 alpha, 3 alpha, and so on from multiple cover contributions or unions of disks do you expect to see as you cross this wall. And you should raise that to some power, which is the intersection number between the boundary of your given disk and the wall. It tells you how many ways, combinatorial, it's a combinatorial factor. How many ways do you have to attach on a disk of class beta the stuff that happens at the wall? And each Z beta gets changed by that. And because these operations are multiplicative, this is a well-defined automorphism of a piece of a complex torus. Sorry, not complex, algebraic torus or something, analytic torus. And then the corrected mirror will be obtained by regluing the local pieces along these coordinate changes. And then this superpotential will again be a globally defined analytic function. So one of the tenets of mirror symmetry for log-Calabi-Yau's is that these wall crossing transformations, there are all these possible walls that can happen in different places, and these walls should satisfy a cocycle condition. So what I think this was first articulated very carefully by Kontsevich and Soibelman. The statement is there are lots and lots and lots of walls around because there are lots of ways that Maslov index 0 disks can happen. But if you look near some place, any place you want, and you find all of these wall crossing transformations along a loop that avoids the nasty point where you don't really understand what happens anymore, then the product of all of these transformations should come back to identity. The proof of that is the analysis of how Maslov 0 disks themselves break into pairs of Maslov 0 disks. And so this consistency is actually the basis of an algorithm that's used to construct the mirror by basically finding, in fact, all of these wall crossing transformations just from the generating data of the singularities of a Lagrangian torus fibration. And unfortunately, the problem is that consistency fails when there are negative Maslov disks. The reason why it fails essentially is that now Maslov index 0 disks don't have to break into pairs of Maslov 0 disks. They can also break into a positive Maslov disk with a negative Maslov disk. So, from that perspective, my whole talk is kind of trivial. It's just to remind you that 0 can be something other than 0 plus 0. It can also be positive plus negative. There's only one thing you remember of this talk. This is probably it. Okay, so that said, so I wanted to show an example of this phenomenon because it's kind of more convincing when somebody tells you, doomsday is coming, if you can point to what's going wrong with your world. So the example I want to walk through is a blow-up of a toric four-dimensional thing, which is the product of C squared with what I've called the canonical bundle of P1, which means the total space of a line bundle of degree -2. So, and I will blow this up in two places. Let me show you more stuff so that it can make more sense. So, as toric varieties, C squared is just, a quarter plane. O of -2 over P1, it's this infinite trapezoid shape, where the zero section here, down here, is a sphere of normal bundle -2. You already see some kind of borderline holomorphic spheres coming up, right? I mean, that's done on purpose. And I will blow this up in two places. So one is I take a line 1 times C, so first coordinate equals 1, times the fiber at infinity. So it's like this piece of a toric boundary. I'm thinking of my base CP1 as having 0 here and infinity here. And then the other blow up is in the other direction, C times 1 times L0. And you could say, well, why did you choose 1 on the first factor? If I had put my lines at 0, then this would be a completely toric variety, and then I wouldn't have any problems. Sure, so the example is slightly artificial. But just like in the case of, for example, CP2 or C squared, we can see things about Chekhov tori and other interesting Lagrangian tori by pushing ourselves to a non-toric picture. Here we see something more interesting by going what in fact would be a toric manifold if I hadn't put my blowups off of center. So in particular, so then at this point I'm kind of on autopilot, and you guys have no chance of really like catching up on all the details, because I spent kind of 10 years of my life studying Lagrangian fibrations and blowups of toric varieties and how we do Floer theory in them. So I'm going to tell you what happens, and you can read through the paper if you want the details, but I don't expect all the details to be followable. So the basic thing you should know first is the first Chern class. You can represent by the proper transform of the union of all the toric divisors under the blowups. And then there's a Lagrangian torus fibration whose base still looks like the interior of this moment polytope. But you should imagine, okay, so this still has a T2 action on the last 2 factors, but the first 2 factors I've messed up the torus action. So you should really imagine, in fact, that I'm going to build a Lagrangian torus fibration which is T2 invariant. So it is true that every fiber lives at a particular moment map value on this side, on the trapezoid. On the C squared side, so I'm cheating. I'm actually going to use product tori by fixing the radius of the norms of the coordinates, Z1 and Z2. I think I'm going to call them X1 and X2. So it's still like product tori, but product tori where you fixed the moment map in the last 2 factors and you fixed the actual norm of the coordinate in the first 2 factors. And really, away from the exceptional divisors of a blowup, these are just going to be lifts of product tori. So let's just ignore the exceptional divisors mostly, except where we need to remember them. Think of these as product tori, just lifted to a blowup. Okay, so at this point, it would be good to remember what is the story for the thing before we blow up, because we're going to modify that. So if I look at a product torus in C squared times O of minus 2, I need to look at what disks it bounds. The simplest ones have Maslov index 2. They are the ones that hit exactly one of the toric strata, which means one of the coordinates vanishes once. And therefore, the others have to be constant. So, for example, you might have a disk along the x1 coordinate axis. You might have a disk along the x2 coordinate axis. And each time I write a disk, I'm going to write its weight. And so I'm denoting by Z1 and Z2 the Floer weight of those 2 disks. They are 2 of my 4 coordinates on the mirror. And then similarly on the other factor, so now there's disks that are constant on C squared, and instead in O of minus 2 hit one of the 3 toric strata. The simplest one is just inside a fiber of my line bundle O of minus 2. I will call Z4 the weight of that one. And there's 2 others that go towards the fiber at 0 or over infinity. So they're sections over a disk in the base CP1 of O of minus 2. Their weight you can calculate, choosing conventions and so on. And then there's one more guy, because this green sphere, the 0 section, has normal bundle O of minus 2. So it has trivial Chern number. Its normal bundle is O plus O plus O of minus 2. It has C1 equals 0. If I attach it to a disk, that doesn't change the Maslov index. And the claim is this downward disk, Z4, union this sphere, even though the sphere itself is not regular for the standard complex structure, the union of the disk and the sphere is regular as a stable curve, which means if you deform J a little bit, then you will actually see a holomorphic disk forming, obtained by smoothing the node. And you can carry out that analysis very explicitly. This is not some place where you need fancy technology. This is playing by hand with co-kernels of Dalbar operators, if you want to. Okay, so for everybody, we have this formula, which is whatever it is. So now we are going to redo that in the blow-up. And so first thing we'll do is we'll say, okay, when does the picture change? And the answer is the picture will change essentially when the radius of the tori in the c² factor get bigger than 1. If they're less than 1, by the maximum principle, in fact, nobody can notice that anything is happening because the blow-ups have happened farther out and your disks are not going to go there by maximum principle, and they just live in something that doesn't know you've done any blow-up. So you'll get the same formula as before. But as you increase the radius past 1, then you actually have a change happening. And the reason there's a change happening is because you may have disks in the, so maybe I should on the side here draw something. In a c², if I blow up a point, say 1, 0, that's off center. If I look at the product torus here, it still bounds just the disks going to the 2 coordinate axes. These are the simplest ones, the only ones that, I mean, of course, there's higher Maslov index disks that have higher contact orders with the axes. But then if I go past radius 1, then there's something new happening because I can take a part of a complex line passing through the point that I blow up. It will hit both coordinate axes. So it has Maslov index 4 before I blow up. But after I blow up, here it no longer hits the divisor D, and Maslov index has gone down back to 2. So the same thing happens here, but in higher dimensions. And for example, sorry, I think this one is the one I wanted to show first. If I increase the radius in the second factor past 1, so past this blow up, then now I start having disks that arrange to pass through, for example, so what's the main term here? I think the one I liked to show off is this one. This is one of the new terms. This is a disk that it comes from this disk here. It has the Q, Z3, Z4, but it arranges to also move along the second factor here. So it also picks up a Z2, but it does it in such a way that at the time when the green disk hits the toric divisor, the red one is actually passing through the line where I did the blow up. And then for the same reason, Maslov index stays 2, and I should count it. This Q prime, sorry, what were Q and Q prime and so on? These are shorthands for T raised to certain powers, which are the symplectic areas of certain spheres in my space. Okay, so depending on, I never told you exactly how big I made my 0 section sphere, for example. And the answer is I make it so that its weight is Q squared. So Q is the weight of 1/2 of my 0 section sphere. And Q prime and Q double prime will be the same thing after blowups, which eats some of the area further. Okay. So there's that. And then here there's another funny term. That one is a disk that goes along Z2 and Z4, but after I do Z4, I attach this sphere, and I arrange that all this happens exactly at the point where I was passing through the blowup. So this eats a sphere of actually negative Chern number now. If I take these spheres S and I place them at points where I was going to do the blowups, I made the normal bundle even more negative. This is a sphere here with normal bundle O of, first factor is triggered, so O plus O of -1 plus O of -2. So it has C1 equals -1. This is a Maslov 4 disks union a Maslov -2 sphere, contributing to the count of Maslov 2 disks. And I claim these are the only ones that are regular. I mean, of course, when you see negative spheres, you need to ask, well, what about multiple covers and so on? And you can show no multiple covers here. Okay, and then you can repeat that in all the regions. And the weirdest of those terms is the one in orange here. That happens when both radii are positive. So this one is in fact a disk that goes in the Z1, Z2 coordinates simultaneously. It has Maslov index 4 in the first factor, together with this Z4 disk here. but we arrange that when this disk passes here, it's exactly at the point 1, 1 where both blowups have happened. So that this sphere here hits exceptional divisors in 2 different places, and its normal bundle is even more negative. It becomes O of -1 plus O of -1 plus O of -2. So this is a Maslov 6 disk with a Maslov -4 sphere, and it's there. And it's the root of all of the problems we're heading into, in fact. Okay, so then you can test your theory about wall crossing, and you can ask, well, how do I connect these things together? And so by studying what happens on the walls, so the walls happen exactly when R1 or R2 is equal to 1, the radius in the first or the second factor. And you can look at what kinds of Maslov index 0 disks happen there. It's again the same kind of story. You look for disks that kind of happen to pass through the exceptional divisors at every place where they would have otherwise hit D, or ways to attach creatively some negative Chern number spheres. And okay, it's full of formulas all over the place. What happens with each of those is you know in advance that the wall crossing transformation is only going to affect either Z1 or Z2, because this is the only way in which bubbling happens, basically. And then I hate trying to count Maslov index 0 disks, because they always have multiple covers. I never know what to do with those. So instead, there, what you do is you compare the counts of Maslov 2 disks on both sides. You know what shape of transformation you have. It's only going to affect Z1 times something involving the others, and you solve for what this is. And then afterwards, you can justify, yes, I can see all these disks. I have no idea how to tell you that there are no further contributions from multiple covers, except that by comparing, this is what must happen. And then we have a problem, because you can compute now the product of all of these coordinate changes, and you don't find identity. Okay. And it's not a bug, it's a feature. And the reason is that at this middle place, radius 1 for both things, I can just take this disk Z4 that goes straight down, and then this sphere, which had this very negative normal bundle, and this is going to be a stable disk of Maslov index -2, which is generic. Now, it's not generic for this particular position, in that if I perturb J generically, it might move to a slightly different place, but it will still be somewhere. There will still be a codimension 2 set of fibers of my fibration, which bound this kind of disk, or rather some smoothing of it once you deform J. So now we have to decide what is the geometry of what we get. Okay, so first claim is this thing here is consistent up to the orange terms, except one orange term was no longer orange here. This is orange. Okay, so the orange terms are the only ones that cause our life to be miserable. If you ignore them, just pretend they're not there, then everything is consistent and would agree with what other calculations in mirror symmetry would tell you to do here. So if I work mod these terms, which I can do formally by setting q prime q double prime equal to 0. That's, by the way, the weight of that very special sphere with the very negative normal bundle. Then things are fine. And then I can treat those terms as deformations of the geometry. So they're deformations of the geometry which modify a bit the function in this sector. They modify this coordinate change and that coordinate change. And of course, they modify the consistency of the coordinate changes. So the claim is now we can use actually abstract deformation theory to understand what's happened. And one way to state that for people who do mirror symmetry is you have deformed, the previous thing had a Landau-Ginzburg model as mirror, which means this space x check and this function w, which were perfectly nice and consistent if I forgot the orange terms. And then I will deform them by a class in Hochschild cohomology. That's how, when you don't know what to do in life geometrically, you just, say, okay, I'm going to do some algebra with my space. I will look at Hochschild cohomology to see how the algebra deforms. It turns out Hochschild cohomology of Landau-Ginzburg models has a geometric interpretation as the cohomology of polyvector fields. So that's the same thing as deformation theory in usual, complex or analytic geometry, but modified by adding a term of interior product with dw into, acting on polyvector fields with degree -1, that you kind of contract with a differential of your function w. And so the deformation class we want is a class, in fact, in HH4 if we use the correct. No, sorry. Let me not tell you what degree it's in, because I don't want to tell you what the grading is. Anyway, so the leading order thing is a term in, so I'm going to think of this as check cohomology, because I have coordinate charts and I'm gluing them together. This is kind of calling for check to be brought out. And then a check 2 cocycle is something that looks at a triple overlap. Well, I had 4 things together because of whatever, but it was really like around a codimension 2 thing. So you can make that into a 2 cocycle with coefficients in the second exterior power of a tangent bundle. And the claim is the magic value. So this was the weight of my weird disk. And this quantity here tells you that the inconsistency is going to go in the Z1, Z2 directions. And then, well, you can say, oh, wait a moment. In this complex, this is not going to be a cocycle because it's not closed under interior product with dw. How do you make it a cocycle? You complete it by adding more terms. You add in a 1 co-chain whose values on the overlaps, exactly the places where you had those orange coordinate gluing modified, were going to be these vector fields. These vector fields are exactly by how much the extra orange term modifies the coordinate change. And you are going to add also something that's a 0 cochain, which means it's functions on each piece. And here, just on the plus piece, we add the orange term. And then you can check that with all this data, this indeed becomes closed because interior product of dw into this beast gives you exactly the check co-boundary of these guys. And interior product of dw into these guys gives you exactly the check co-boundary of this piecewise function. And so the slogan here is that what you have is what I would call a deformed Landau-Ginzburg model, where you have a locally analytic function on a locally analytic space, and the coordinate charts are still glued together analytically compatibly with your functions, but they don't satisfy the cocycle condition anymore. And in the zoo of strange exotic geometries that people study, I mean, most people I tell this to, they kind of come to me and, have you heard of gerbs and things, and have you heard of Poisson bivector deformations and so on? And I think this is not either of them. This is in the same spirit, but it doesn't work the same way, because we don't deform what cocycle conditions functions have to satisfy, but rather the coordinates themselves. Okay, so anyway, that's the slogan. Okay, so that was an example. I'm going to pause briefly for questions, and if there's still a tiny bit of energy, I will tell you a bit of a story of how this fits into a general picture. And that general picture is more conjectural. It's not like I know exactly.
I have a question.
Yes.
So on the previous slide, so there's these nodal negative index things and there are multiple covers. Suppose by some magic, you know how to glue all of them. Then would that mean you can construct the mirror directly? Would it tell you more information, or it's already kind of?
This is the mirror. This is the actual answer. Okay. This is the actual answer. And just what I cannot do from these formulas and these inconsistencies is tell you exactly how many Maslov zero disks there are in each class, because this is probably something actually exponentiated, including unions of multiple covers of Maslov zero disks. But this is like how to account for them in the right way for this. This is the formula for this example.
Okay.
Okay?
Yeah.
Yeah. All right. Okay, so here's a proposal for how we might think about, how to build mirrors and so on in this setting. So, and the proposal is basically to go along the lines of family Floer theory And you're only going to see part of that story here for reasons of time and what we need to do. But so let's say again, we start from our Lagrangian torus fibration and we look at the smooth fibers and we look at what we have. And let's talk a bit more, let's go algebraic. So the coefficients with which we'll do Floer theory, we've said we are going to use these Novikov weights, but these Novikov weights depend on the local system, which means for a given point of a base B, in fact, I end up having coefficients which can be any kind of monomules in these coordinates z1 zn. If you want, these weights z beta are going to be monomules, Laurent monomules in this. And then the coefficients we have, of course, will be linear combinations, infinite sums of those, subject to the finiteness condition as usual for Novikov. So in fact, the coefficients we should be using, if we just think of a tori, are some kind of universal coefficients that put together all of the local systems you might have. And these coefficients are going to be a completion of the group ring of H1. If you want a completion of Laurent polynomials in Z1 Zn, where the completion condition, so the claim is this forms actually a sheaf on the base of a fibration. On a given small open piece, what coefficients might you have? Well, the coefficients you should consider are power series, Laurent series in these variables, such that if you evaluate at any point in your given open, you satisfy the Novikov convergence condition, that the valuations go to infinity. Okay, so anyway, this is just a gadget for recording what kinds of weights can actually happen in real life. And so now what you can do is you can try to do Lagrangian Floer theory for holomorphic disks, not just with values, with boundaries on a single fiber, but instead on a moving fiber that's allowed to vary as it wishes, and with these universal weight coefficients. And the claim is that you should be able to develop a Floer theory that produces curved A infinity operations, Floer-Theoretic operations, on simultaneously all of those. And therefore, that means the incidence conditions you might put, if you think of it naively as pullback incidence conditions push forward, incidence condition will be not a chain on the Lagrangian, but instead a chain on the base with coefficients on chains on the Lagrangian, saying, I want my input mark point to be in one of these fibers and with boundary on that. And representing some cycle on that fiber. And so you can try to write an M0 operation like this, and all the MK operations, just by whatever you did before. I'm not going to try to do this with actual chains and Cohen-Ishii structures because I'm really bad at that. Instead, I will tell you maybe there's time about a more theoretic version of this that I think is easier to set up technically. But the point is you can basically define a Floer-type algebra, not just on cochains on a single Lagrangian, but instead on the family of those over the base, with coefficients in this funny thing. So assuming you've done this successfully, what do you expect the M0 obstruction to do? So it will count all holomorphic disks with boundaries on all your fibers in families. Well, so first I expect that this will be a sum of terms whose degrees are different depending on what Maslov index we see. So I expect there's a first term alpha 0, which will be in C0, so it's just a function with coefficients in H0 of a fiber, which means just again numbers, but really in O, and so that means really a function. This is going to be my count of Maslov 2 disks through a generic point of a generic fiber. And those exist everywhere, and they will do what they do. But of course, they may jump from place to place across the walls, which is why here I put, cochains, not cocycles. Here I was bold and assumed cocycles. Then alpha 1, Maslov 0 disks, well, they will live in codimension 1 in the base, and they should occur in codimension 1 in the fiber. And Maslov index 2, minus 2 disks, I expect happen in codimension 2 in the base, codimension 2 in the fiber. Why do I expect that? Essentially, this should follow from the tropical limit in geometry. You expect these disks to live along complex codimension I subvarieties. And when you are near the tropical geometry limit, codimension I complex things live over codimension I in the base, codimension I fiberwads. And the other thing I expect, actually I'm not the first one to expect that, but they say that for one Lagrangian, and I'm just doing all the Lagrangians at the same time, M0 should satisfy something called the master equation or Maurer-Cartan equation, which says, so delta here is a classical boundary, and if you believe the first part, the classical boundary is in the sense of this one, like how this varies in the base, basically, should be given by some kind of bracket of M0 with itself. It says the boundaries of moduli spaces of disks are, after all, moduli spaces of pairs of disks. Okay. So assuming this, assuming this, my pen just is telling me that it's almost trying to end, but I still have a few minutes. So assuming this, you can ask, okay, if I have this way of recording codimension I walls of Maslov 2 minus 2i disks, where do I go from there? And so observe there's a natural bracket on this strange space, which is cohomology of a torus, tensor product with Laurent polynomials in its first homology, which is what this ON is about. It's completion of that. That bracket is basically when I have a monomial times a cohomology class and two of those. What I do is I use the exponent of one monomial to do interior product into the other cohomology class and vice versa. So this is a degree -1 operation, skew symmetric. It's a shifted Lie bracket, and it doesn't come out of nowhere. I mean, for me, it came out of what I wanted to get afterwards, but actually then I kind of unpacked, I mean, Mohammed pointed out to me, I think, the connection long ago, but I was slow to see it. This is actually the Chess-Sullivan string bracket on the homology of a free loop space of a torus. The homology of a free loop space of a torus, well, there's as many components as there are homology classes. So you'll get this group ring from just the components, and then each component of a free loop space looks like a torus, so you get the cohomology of a torus. And the string bracket on that, on the loop space, so basically you look at chains in the loop space and you look at where you can insert one loop into the other one or vice versa, is exactly this operation. Okay, so we're going to extend this from just these guys to co-chains on B with coefficients in that by combining with a cup product on B. And then we have a big algebraic beast, but that's the beginning of the end of the tunnel, because H_1 of a fiber is the same as the tangent space to the base in a Lagrangian fibration. And that means, in fact, that this strange thing here, like monomials times cohomology classes on the fiber, that's actually the same thing as polyvector fields on this mirror space. How? Well, so basically, here, like each class in H_1 dual to our favorite basis element of H1 of a fiber, you can turn into a vector field, dd log of the corresponding coordinate on the mirror. And that's just that. And this is actually transcribing these things into polyvector fields on the mirror. So transcribing in this way, you get a sum of cochains on the mirror space with coefficients in exterior powers of a tangent. This weird bracket up there has a name under this dictionary. It becomes the Schouten-Nierenhaus bracket on polyvector fields, which is like the extension, it's the multilinear extension of the Lie bracket of vector fields. And then the master equation becomes an equation of the same shape about this guy, which shows up in deformation theory of geometric structures all over the place. So the slogan is, under these various optimistic conjectures about the shape of M0, we end up with some quantity on the naive mirror space, which solves this equation for the Schouten-Nierenhaus bracket. And that's the same as saying that if you take the usual check differential, I'm thinking check, but you could also use Dolbeau or whatever, and you deform it by bracket with W, this is again a differential which squares to 0. And so you can expand this, term by term, because we are not used of thinking of this like extended thing with all sorts of grading mixed together. And this is what it looks like degree by degree. And what this suggests you should do is you should think of delta plus the bracket with W1. So W1 is the one that counts Maslov zero disks as a deformation of the analytic structure. So this is what people have been saying. Maslov zero disks, you should change your analytic structure on your mirror space. So if you're using, if chains here, you think of check cohomology, this means you deform the gluing between ui and uj by a vector field, which is the value of a cocycle on that overlap. If you're thinking of Dolbeau, you deform the del bar operator by W1, which will be now a 0-1 form with values in the tangent. So this first equation here says W0, the thing that counts Maslov 2 disks, the superpotential, is analytic with respect to this deformed structure. The second equation, however, says that this deformed structure is not an analytic structure. This doesn't square to 0. It fails to be an analytic space by this amount, interior product of d of the superpotential into the next term, W2. And this is, again, breaking into Maslov 2 plus Maslov minus 2. So interestingly, if you stay in the check world like we've done, it says this measures the failure of coordinate changes to satisfy the cocycle condition. If you're in the Dolbeau world, this is much more exciting. This tells you about the failure of del bar to square to 0, which tells you, in fact, the deformed complex structure is not integrable, but instead has a Nierenhaus tensor prescribed and equal to this quantity. Now, of course, you have to be a bit optimistic. I mean, there is such a thing as non-Archimedean Dolbeau cohomology and so on. I haven't thought about almost complex structures in the non-Archimedean world, so I don't know if this works, but it's kind of interesting. And the thing that reassures people in real life is what you care about is the critical locus of a superpotential, and that one is still honestly analytic, because along the critical locus, the perturbation term vanishes. So you can still do geometry with this if you really want to. And last but not least, for there to be negative Chern number, the negative Maslov disks, you can't be in a Calabi-Yau. So people who only care about mirror symmetry for Calabi-Yaus, this is not going to happen. So there's kind of various restrictions on when this happens. But anyway, the story is, in general, life is actually more exciting than I thought. Okay, I think I should stop here. Thank you for your attention.
Thank you very much. Let's thank Denis for his very, very interesting talk. Thank you. Are there any questions from the audience? Joseph, please go ahead and unmute yourself.
Can I ask a question?
Sure.
So if I'm interested in like the other direction, like if I want to study like Landau-Ginzburg models mirror to like log Calabi-Yau, say, what should this story tell me?
So you mean if you want to do symplectic geometry on the Landau-Ginzburg side and complex geometry or algebraic geometry on the log Calabi-Yau, I think this says nothing. I think there's no change involved there. So I think you should, for the purposes of the other direction of mirror symmetry, where I think nothing happens there. This is not relevant to the other direction of mirror symmetry. This is purely a weird deformation of the A model or symplectic geometry of your log Calabi-Yau, which causes a weird deformation of the B model of the mirror. I mean, in some sense, optimistically, if you use this like modified, this Dolbeau picture, and you say, oh, the mirror becomes something with an almost complex structure, well, that's going to be important for what you mean by matrix factorizations and so on and so on. The Fukaya category is fine with an almost complex structure. It will not notice the difference with a complex structure.
Okay, yeah, that was my impression. Thanks.
I mean, also, on the case of like complete intersections in toric varieties, where Mohammed and I have this not written second paper giving candidate mirrors. We have old paper giving candidate mirrors, but we have an unwritten second paper proving mirror symmetry. I claim that proof is completely fine. We are able to prove HMS between complex geometry on the complete intersection or the blow-up versus the Fukaya category of a mirror with no trace of this happening. So I think this is fine.
Any further questions?
Yes, may I ask a very naive question? I guess the torus fibration is not determined by the manifold. So what happens when you change the torus fibration?
That's a very good question. So certainly not determined by the manifold. It's slightly more determined by the pair x comma d, because, well, okay, it's not exactly determined, but its general features are determined. For example, the Euler characteristic of x minus d and the higher Chern classes tell you about the amount of singularities of various kinds that must be present in the fibration. For example, people say on a K-free surface there need to be 24 singular fibers because Euler characteristic is 24, and that sort of thing.
Yes, but how does the how does the x hat change? Is it known that
in practice, x hat usually changes by crepant birational transformations. So concretely, what I can do, for example, is I can deform things so that two kinds of singularities will cross each other, and the mirrors I will build will then differ by contracting something and blowing it up differently, or something like that. So what's a good example of that? Yes, okay. A good example of that. So let me just make it. Wait.
But so that happens if you have, if you have an explicit deformation of one torus fibration to the other somehow, with whatever explicit deformation means with respect to singularities, of course. But
so yeah. So here's an example on T star S3. Okay. So T star S3 is a quadric Z1, Z2 plus Z3, Z4 equals 1 or whatever inside C4. And so I can project to the complex plane by just projecting to say Z1, Z2, for example. And there's two bad values. The general fiber of that is a product of two cylinders. And then there's two fibers that are cylinder times cone and cone times cylinder. So not a union of two lines, really. And depending on how I slice this by, so I will slice this by Lagrangian Tori, which are product here, but here I get to choose, will I cross one then the other or in the other order? Okay, I can move, if you want, my singularities around by something. So what the mirror will produce is if I cross both singularities at the same time, producing a really horrible situation, in the middle, then the mirror will become something singular, which is going to be, in fact, Z1, Z2 equals Z3, Z4 inside C2 to the 4. This is what's called sometimes the conifold. It's like the thing that you get by contracting the zero section. In fact, this thing is almost, once you contract, it's almost self-mirror. And this has two small resolutions. So torically, this looks like an Egyptian pyramid. And the ways to resolve it are you kind of, instead of building the roof of a square house, you deform to a roof of a rectangular house. And there's this way, or there's the opposite way. Sorry, this is a horrible picture. These are both the total space of a line bundle, vector bundle O of minus 1 plus O of minus 1 over P1. And there's a, what's it called? Atiyah flop relating those two. So these are both equally good mirrors of T star S3, except I need to delete something, T star S3 minus a divisor, or this with a superpotential. They are both equally good. There's a bunch of conjectures in algebraic geometry proven in these cases, saying when you do crepant birational transformations, your derived categories and all the algebraic geometry transfers nicely by, there's in particular derived equivalences. And so these are all interchangeably good mirrors. Sorry, so this is like length into one example. In all known examples where you see things you can vary, the effect of varying them is these kinds of crepant birational transformations, where you contract something to blow it up differently, and the algebraic geometry doesn't change. I mean, it changes if you get attached to details like what are points and what are lines, but the derived world doesn't see it.
Somehow I think you said something which was the untold part of my question. Can you actually see more than the derived category of coherent sheaves?
So I guess basically
so intrinsically is something more. Is there something more defined than this?
So I don't know exactly, but one small thing to note is the derived category of coherent sheaves of a space doesn't know which of the sheaves are the points, the skyscraper sheaves of points. And essentially having chosen the fibration rather than just up to various things is kind of like singling out, these are the tori that I will think of as points. And if you deform your fibration in a non-trivial way, you can get slightly different kinds of tori, which are equally valid objects of the Fukaya category and are actually the points of a slightly different mirror. But the derived world, the Fukaya category and the derived category of coherent sheaves don't notice the difference. So I think
yes,
there's also something in the language of like stability conditions or stuff like that, extra geometric structures on derived categories that will tell you what it means to equip a derived category with enough data that you can go back to the geometry from there.
But you don't know exactly which geometry you go back there. You can go back to several geometries, as you just showed.
Several, if you didn't choose your fibration, yeah. Once you've chosen the fibration.
No. And if you don't choose, if you look for something intrinsic, but I don't want to take all your time. Sorry.
No, it's okay. But if you're intrinsic, then you go back to SYZ, who said, wait, you should be doing full Calabi-Yau, and you should have a holomorphic volume form and look for special Lagrangians. And that's what rigidifies it. So the holomorphic volume form, by singling out special Lagrangians, chooses one fibration. We don't know how to build it, but there would be only one if there's one. Okay. And but that's actually relevant because that holomorphic volume form is believed to also give a condition on the Fukaya category. And on the mirror side, this is like choosing also a Kahler form on the mirror, which gives a stability condition. And once you choose the Kahler class, you've singled out which of these mirrors you want. And the reason is basically in this flop example here, you have a P1 here, and you have a P1 there. Morally, they represent opposite homologic classes of each other. So one picture is when you want to give this thing positive symplectic area, and the other one is when you want to give it negative symplectic area. You should contract it, resolve it the other way, and give positive area to that one. Anyway, so I think there's a picture around there, but I don't know it very precisely.
Okay, thank you very much. Thank you.
Perhaps we thank Denis again for his talk and pass to the more informal discussions. So thank you, Denis, very much.
You're welcome.